Okay, so now we're going to start the class. Before I gave some examples, or just the one toy example, now we're going from ground zero up. And these first two lectures, I think I said before, what we're going to do is really talk about these governing equations that we're just going to study, that we're just going to simplify. So I think it's important that at least once that any reasonable fluid mechanist should see really everything that goes into developing these equations, right? Because that's important because then you'll know the assumptions, right? And all the mathematical terminology that makes it true, or why you're going to believe these equations are modeling a fluid, or at least give you some tool to tell you what the fluid will do in the future. All right? So I want to kind of take a naive approach to this subject, right? Where if you just had no idea what you were going to do, you just started from the basic assumption, in fact, that I want to study a body of fluid in motion. Okay? I think I have these thinkings, right? I want to study the motion of a body of fluid, right? However you want to say it, right? That's what you're starting, right? You just know that I have some wiggly thing of fluid, and you're asking, how does it move? Big question mark. That's what you're trying to answer. Okay. So I want to break just that statement down into something. And, right, really you're asking, right, the key words there is we want to study, right, some body of fluid, and what else do we have? Right? Motion. Okay. And then even that last topic we want to study is fluid, not some solid piece of aluminum or something like that. We're saying we want to study a body, motion, and fluid. Okay. So each of these words has a more specific meaning we can give it to if we're going to use math to describe it, right? So what does study mean? How could we make study a very specific thing? Well, at least I put forth what that really means is to have some coordinate system, right? Now, it could be a bunch of ones that you've seen before in your physics classes. What I'm saying, if we want to study something, what we really are saying is we want to both agree on where things are at a certain time, right? Even like relativity and all those fancier subjects, right? They went down to the basic assumption of this: how are we studying something moving? Well, before they thought time was independent, so then Einstein's special relativity come along going like, no, I actually have another coordinate called time. So this is a fundamental thing, and that's how we can study complex objects through math, right, and calculus. We have to establish some coordinate system so that two observers, you and I, both agree on something that we're modeling through our equations. Okay? Next is body. How can I more define body? Well, if I have a coordinate system, right? So, right, a body, I always use capital omega, is right. It's really just a set of points. Somehow you've defined them, but the idea is mathematically, coordinates give you a way of creating points. Let's say x, y, z, and even a t, but this doesn't depend on the other. So usually sometimes you say it like this, but the idea is like the coordinate system gives you this ability to put tags on every little parcel of fluid or continuous thing we're talking about. And then the body is just labeling each of those things in a special way. One other concept about this body is it could have a boundary. Right? Keep in mind, it doesn't have to be an entire space of points. You could cut it off, right? You could cut off your set in a certain manner, and that would be a wall, let's say. But we're not there yet, right? We're just saying the body, set of points, could have a boundary, right? Okay, then what does motion mean? Well, you know, this is people contend that Navier Stokes really isn't. You can't understand it through, I don't know. But the idea is motion, I'm going to say, right, is really Newton's second law, or Newton's laws. Right? And why am I saying that? Well, right, motion, you have to bring in some concept from physics, right, of change, rate of change in position based in time, or rate of change of anything, right? And I'm just saying that, well, I'm in the world of like right? This is what you mean when you say that. You're saying that, like, really, I'm saying everything I'm going to talk about, right, of this body of fluid is in classical mechanics. I don't need any quantum concepts. I don't need any relativity concepts. I don't even, you could use statistical concepts, right? But then again, appreciate that these wouldn't change, right? But what did change is how you talk about motion, right? So let's say you could be right? This is where that assumption would change, is this idea of how you're going to prescribe motion is this idea of a statistical mechanic idea. But that's not this class at all, right? We're going to do the classical mechanic idea where we're just going to use statements that are formulated in terms of Newton's second, first, and third law, right? Really, they're all in there, but really it's the second law we care about. And why we care about that is because that law is what prescribes motion, right? Newton's second law, what does it say? Newton's second law says forces, right, motion. That's what Newton's second law is a statement about. It's saying forces prescribe motion, or motions prescribe forces. And then the last one that maybe we've never seen before is this idea we have to rigorously or just somewhat define exactly what a fluid is. Right? How is a fluid different from a solid? Okay? And that would be something maybe you've seen before, or maybe you haven't seen before. And we can kind of describe it later, but like really, if you just did experiments and looked at how things are deforming, et cetera, right? The idea is that a fluid, it can't support a shearing force. Hopefully you maybe done mechanics before in your engineering classes, but you know that a shearing force is that tangential surface force. So for any sort of body of fluid, we kind of recognize the fact that a fluid's different from a solid, and that is solids can support shearing forces, right? And what this is actually saying, right, what makes it a fluid in the motion is that equilibrium will only right? This idea that there's an equilibrium of that equation right there. And what makes it a fluid is you're saying there's only going to be an equilibrium solution, right? No time dynamics anymore, as long as there's no shear. Right? The difference of a solid is a solid can support a shearing force. Right? And I remember this always, because that's always given to you. You're always sort of told that off the bat later on, going like, a fluid can't support a shear force. And at least I always remember that reasoning is right, really saying right, that you can't right, really that's just saying you can't stand on water. Now, right, I mean, Jesus walked on water or however, I don't want to offend anyone, but right, the idea is like it's a statement about that. If in your mind you have some pool and you filled it up with a solid, right? And then you stood on that solid, right? You'd have a force down, and everywhere around here, right, there'd be shearing forces, etc. But like, let's say if it's a wiggly solid, or maybe like a piece of rubber, which is an elastic solid, but a solid's still the same, you would deform, let's say it even looks like this. Okay? And there would be just some finite displacement due to a shearing force, and the shearing force coming from your weight. But the other way is if you, right, you clearly accept that if I had some liquid in here, right, and you jump down, you have some force going down, and it gives you shear forces around your feet, etc., which develop into more shear forces, and you just go right through, right? So then your guy, right? You get there, you have your force, and then eventually, splashy, splashy. Oh no, I'm falling in. And then more so, once you're in the water, there's no more shear forces, and the equilibrium exists. Now, already from that concept, this is a liquid phase, solid phase, right? Same reasoning is the idea that a gas is also a fluid. Some gas can't, right, support some shear force either. So already you have this idea of like, I kind of have a better sense of what a fluid is for what I'm going to try and model right now. And that's a topic that you should always remember, is that the fluid can't support a shear force. There's no equilibrium unless there are no shear forces. It wasn't the case in the solid because your weight was providing some shear force around your feet, and it just gave you a finite displacement. Okay, so that's an overview, but now let's get into each one of these points I want to think and just kind of think about them, reason them, and dig deeper, right? Study coordinate systems. So we want to prescribe coordinate systems. So what are some coordinate systems, right? Okay. Right? There's some classic ones. Right? There's the Cartesian coordinate system. Right? And that's x, y, z. It's one of my favorites. I can always kind of see it, imagine it. It's really great properties about it. But again, let's just kind of think about what does it mean to have for a Bernoulli coordinate system, or at least the Cartesian one, right? So here's my Cartesian coordinate system, right? It's really this, right, this little boxes I can draw, and I can just draw these, right, nice orthogonal, and all of them are, and I have like a z direction, an x direction, and a y direction. And really these end up being vectors, but again, you have this little right-hand thing for a Cartesian you can always do, and it just extends right out. There's nothing stopping it, right? So that's sort of something you can already think about. This keeps going on, up and down. This will go forward and backward, and this will go forward and backward. So, right, for Cartesian, we kind of have this, well, that means that all these coordinates, right, they're unbounded unless I bound them. And that's where the boundary will come in when you talk about a fluid. But in just the terms of the coordinate system itself, Cartesian is just all the way, all the way, all the way, right? So if you're going to use Cartesian coordinate systems, you have to bound these somehow because, right, everything's finite, at least in some sense. And if you're saying something's infinite, right, it's really just some sort of approximation. You're saying, like, well, this length is like, looks like infinity. It's certainly a really big number, right? But if you have a Cartesian system, usually you have to bound it something like that. So that would mean like this is some, right, this has some height, right? The z scale, which you saw before. In Cartesian, you'll realize you have to usually assign these types of scales. Right? Now, I'm not saying you could never do, right, some infinite domain problem in the Cartesian system, especially 2D. But you'll see that there are probably like more natural versions of a coordinate system just based on this idea right here, right? That already in your coordinate system you've set up this like infinite, right, that there's no aboundedness. So I at least have to create boundaries in my body. I haven't gotten to body yet. Okay. Classic one, other ones, we have our polar, or really cylindrical. Cylindrical, I can never spell for these things. Okay, so then you have the cylindrical one, which really, cylindrical coordinate systems are established through like a rotation of something, right? Already, what do you have? We kind of kept the z coordinate for a cylindrical coordinate system, right? There is some now kind of radius outright, sort of radial dimension now right here. Let's say it kind of goes something like that, right? And then you kind of have this other one, which you could just draw right here, but usually it's sort of drawn at the very end of this unit vector, or it could be anywhere. It's just perpendicular is the point, that the theta coordinate exists everywhere perpendicular to there. So it's a coordinate system, but there's a symmetry in here. And symmetry, some people describe there's a symmetry that one of these coordinates has, right? If I were to look at this surface or these coordinates, and then rotate the whole thing around again by 360 or 2 pi, right, I get the same scenario. So that's a symmetry. That's kind of too mathy or physical or like sort of theoretical physicsy. But in terms of what we care about, I think I remember it again as, okay, my z sort of unbounded right here. And something else happened. Right? R is only a positive coordinate. We don't have negative radius for cylindrical coordinates ever, right? And that's, you remember, if you look at the equation, right, it has this sort of, if I were to go from these coordinates to these coordinates, the mapping I give is that the radius is a positive number, right? So if you don't remember that, you can always just write out, well, I know the radius is the square root of the hypotenuse. But that sets up this sort of situation here. And you could actually have a 0. Yeah, 0. You include the 0 point. That's the direct center streamline going up. And then, looking at this, here's where the symmetry thing comes in order. I either could say include 0, not include 2 pi, or I could include 2 pi and not include 0. But it doesn't really matter. The idea is, like, look at this. From this coordinate system, I had unboundedness, so I had now to assign all of these. OK, not anymore. My theta, right, you can just say it scales as 2 pi, whatever, but that's fixed for you. You don't really get to have much say over that scale anymore. R now, you have to assign some scale. And then z, right, usually we don't care about that one for a cylindrical coordinate system, right? You really want to key into using your cylindrical polar if you don't care where it came from or going, right? So z is sort of what I remember is that you use these coordinates when you really don't care about where it's going or where it came from. That's a fully developed statement, but again, we can get to that later when we kind of get past this point, right? And if you did assign some sort of scale, right, an L, then you have to talk about entrance effects, because now there's some sort of boundary over here and you have an entrance. But, OK, the idea is now you have to assign a scale, but really you're going to use those if you don't care about where it's going or where it came from. And then there's one more that at least I could talk about. OK, there's obviously the spherical coordinates. And they have these crazy, right, equations that you go over all of their symmetries and signs and stuff like that. But now this one, like that, like that. OK. And then any point on this, right, you have the situation like this. OK. So, right, there's sort of more complicated pictures I have to draw for the spherical case, but you have some sort of sphere, and then I have this as a Lulu angle, right? And this is important that it actually goes from just, right, you're actually just saying about North Pole and South Pole, right? So let's just kind of do it, right? Now, what happens here? Again, there's even more symmetries. It's one of the most symmetrical things you could have. You do any rotation on here, right? And usually it's going to look the same unless you, right, if you color the surface differently, you wouldn't be able to tell. But certainly if it's homogeneous, you wouldn't be able to tell any sort of symmetries. But, right, again, when I think about this, is that now you have this rho, not density. It's just a lot of times referred to as like the rho, or the Greek letter for r radius is the spherical radius. So again, that's not a density in fluid. We're not even there yet. So this density now has 0 and to positive infinity. I can keep growing this and growing this and growing this. OK, but now then, like, look again. What happened? Now this thing, same thing. Sorry, pi. Sort of, right? So now you have the same situation go down, right? Right? Here we kind of eliminated one of these scales. Now we have two of these, or now there's two more symmetries. So it should say, right, very symmetric, right, very symmetrical domain, or I'm talking about a very symmetrical, right, type of, right, we're going to study something very symmetrical. Again, study coordinate system. So if what I'm studying is a very symmetrical thing, or at least all I really care about is some point source, spherical are good. So, right, you're going to always, right, you should key yourself into, you should study something in spherical, right, if it's right, if it's very symmetrical, probably should use spherical. But in terms of fluids, right, it's going to be a lot of gas bubbles, which would mean like vapor problems, right? Or actually, since you can grow and definitely, right, since you can like talk about like an infinite domain very symmetrically, you could in Cartesian as well, but you'd have to assign so many more conditions. This is the only thing that really grows out to infinity right now. You could also have sort of infinite domain problems are kind of usually best suited for this. Right? If everything's very symmetrical, and then you also are talking about an infinite thing, and that kind of clues you into this idea of a gas bubble. Right? You're going to want to talk about a spherical domain, spherical coordinates, right? And there are more, right? There are tons of ways people talk about, right, coordinate systems, tons, right? So even past here, there's another one, right? Right, you can just look them up and just sort of reason them yourself. Like you yourself, I would say, extra credit, right? Right, look up log polar coordinates and do the same process where you kind of draw out pictures and convince yourself what this coordinate system is good for, why you would use it. Or just any coordinate system, right? It's a good, helpful process, I think. OK, so now we have a way to study stuff. If we're studying symmetrical things, we're going to use spherical. If we're going to study things where I don't care about where it's going, where it came from, we'll go ahead and use some cylindrical coordinates. If it's just sort of really a 2D situation, actually, I didn't say that before, 2D, we're going to use Cartesian. Either way, we now establish how we're going to study our fluid. OK, and now let's talk about the body. OK? I think I had this in my notes, but. Great band, by the way. I love The Body. Actually from Portland. Right? Local. Woo! Either way. So now this idea of the body. Right? So what do we do when we talk about a body? Well, let's draw some, right? This we already did it before. Let's see this idea where now something like this, right? Pipe problems. You've seen these before. Maybe it just helps in this context, right? Now my body is actually defined by the pipe itself. OK? So there's fluid flowing in here, and here's my body, right? And the pipe is defined as a set of points, right? What would be that set of points within this coordinate system? Notation. My body, or the pipe, would be all of these points such that the radius such as the radius is less than my radius of pipe. So that's a body. And more so, this is strictly less than. You have then another statement that the boundary of my pipe is when it equals, right, the radius. So these are two sets that we talk about now that we have a coordinate system, there being the actual pipe, which is all the points within my pipe where the r is less than the radius. And then I have this actual boundary, or the wall of the pipe, right? I use this notation for that, where that is defined by when it equals the radius. Now, you've seen that before in some of your problems, right? When you do what? When you say there's no slip at the wall, right? You're making a statement about this boundary of your set, right? The PDE, what we're going to talk about, is describing the dynamics of what's happening before R, but then you set something on the boundary of that body of motion. Body of fluid, sorry. Okay? You could do the same thing, right, if you have a gas bubble. Right? Now I have some rho, or the radius of this gas bubble evolving through time, right? And now this body, right, it now has some, let's say, growth coordinate to it, okay? A little stranger, right? Okay, for my spherical gas bubble that's growing, my body of fluid, or let's say my gas bubble, it's really an interficial thing, which is the example still holds. Now your body's defined still by all this. You might just have this parameter t now, where it's a function. This is also a function, you could say, of R of t. It's just a really boring function. It's the constant function. So these ones are usually more complex because what you're trying to then kind of solve for is the motion happening inside of this body, and then actually even trying to define what that function is of how it grows. So things get a little more complex, right? Okay. So but mostly what we're trying to say is we're trying to characterize the motion of every one of these points within our body, right? Right. This is some tag I've assigned to anything within the fluid, right? There's some sort of tag here. This will be a rho naught. Sorry. Some rho naught, and then a phi naught. There's some other one right here, and that's some rho like 1, right? Same thing if I had some, right, this is that classical law like here, but really there's some point of liquid right here, which is like an R naught, a Z naught, and then a Z naught. Same thing. There's even one right here moving, R1, Z1. They're tags I've given to little parcels of fluid moving down my body. Now the question is, how do those move? And there's kind of two different viewpoints that people talk about of how there's ways to interpret how all of these points of fluid are moving, right? And that's this Eulerian viewpoint, and then the Lagrangian viewpoint. I gotta get better at my erasing in pace, but so there's the two viewpoints of how we're going to define these things. That's Lagrangian and Eulerian, right? Now, what sort of how should you think of these? Is the idea now. There's my sort of space right here. Right, here's my body or region of fluid. Okay, and this is my coordinate system. Lagrangian says I'm going to look at little parcels of fluid. And I always think about looking at the center of mass of my little parcel of fluid because it defines a point within any sort of boundary I describe. So you give me some sort of little region, right, subregion. So we do here. This is like sort of a subregion. Right, there's a whole body of fluid, then I'm talking about a little subregion of that fluid. You prescribe anything that in your head or mind. It defines a surface, and I can define actually a center of mass of that point. So, right, Lagrangian is I take from my coordinate system, I draw a vector, and then I kind of say that is my initial condition. And then as the motion progresses, this follows some sort of path, because I'm only talking about one specific, right? I'm only talking about this x naught. Right? I'm talking about one point. I've locked eyes on this one point. And then what happens is as the motion occurs, as you find the solution to this problem, you find the solution to the motion, which means that this point follows some trajectory and path. Right? So then that's sort of shown like this. Right? And now this is sort of my vector r of t. Right? So really think of this one as some r vector at time 0. I can move along at any time. And also what's tricky about what we have to do now is you have to describe how these particles grow, rotate, stretch, and shear. But we're not there yet, even again, because forces have to do that. But this Lagrangian is talking about paths and how things move along each sort of path. Now that's one path I drew out. Okay? Easily you can understand. Okay, good. You could understand how what you're really going to do is you could assign every point in the fluid domain. Let's just say I put a tag on every single molecule of fluid in here. So I have one here, right? One here, right? Just keep on doing it. Keep subdividing, right? This concept of my region of fluid, I've subdivided so much, right? So this is the whole. And these are bits if you're doing discretely. But limit discrete, limit n to infinity, and well, sort of mathy police will get involved. But like for our sakes, let's just say that's the case, right? That my whole region is broken up to a bunch of little bits of fluid. This could be the molecules, which isn't quite right, but let's just say it is to understand this stuff. I've subdivided a bunch, and you just take a snapshot in time. You assign the center of mass at each one of these points. You solve Navier Stokes, and then you see how they all progress, and then you really look at the paths that they have. So these are integral curves, they say. I'm running out of room. So there's a bunch of lines here. So you've kind of broken it up really into paths. But we'll talk about that later again. So that's sort of the Eulerian. This giant mess of arrows and boxes and stuff. But maybe you can slow it down and see exactly how I drew it. OK, the other way to think of this same thing, have my coordinate system. Okay. Here's my whole region or body of fluid. There's even a boundary to it, but I haven't talked to I don't really care about that yet. But you just have, right, this. Sure, go say there's some boundary. And now what you do is you do the same process, but you don't look at them later on. You keep these you just keep, you just subdivide and subdivide and subdivide and subdivide. And you just fix at each of those points your view forever. So in this case, we had time starting at 0, then we let time move forward. In this case, we just even let time move forward of what we're looking at, right? So this is, right? And then this talks now about properties as the other. Right, the biggest idea of this. So this is a giant set of a bunch of paths, and this is really a vector field for velocity. Right, for pressure and temperature, though, we have a scalar field. Right? And these fields they don't really talk about paths at all. Right? What they talk about is instead, you give me an xy coordinate and a value of time, and I'll either give you a vector or a scalar. Right? Right? So sort of now, you give me, this is like x, y, z of t here at a value t naught. Well, at that time naught, this could be the velocity. And also, as well as in there, at that time, there'd also be a pressure at that moment of time. Okay? And then some temperature at that moment of time. But this box isn't moving. So you can already see there's pretty similar situations going on. That's the biggest idea, is that they're equivalent. Okay? And then, at a different time, t1, now you could say this has moved, actually. I keep fixed at the center of mass, but the velocity of that point has now moved. So now let's say it's shifted downward. And then, in fact, it has now a different pressure and a different temperature, let's say. Right? All this is saying is the Eulerian, right? The Eulerian view is helpful because really it gives us the idea that velocity, the vector itself of each one of these points that I'm looking at in the body of fluid, is a function of any points, of anything in that coordinate system that we talked about, and a value of time. That's what really helps with classical mechanics, is that that value of time ends up being a parameter, and we didn't have to talk about it in the coordinate system. That's classical mechanics. But the idea is, with Eulerian, you say the velocity is a vector field, right? And then pressure, scalar, and then even temperature, right? Maybe sometimes you've heard of that, how, force space, et cetera, is something that's happening, or, right, that function of time, or space-time, right? This is not space-time, this x, y, z, and t. I know that x, y, and z, and t are arising there, but it's not, right? This isn't space-time at all. This is just how you're defining it, right? Space-time is if I, right, brought that also into something that came from the coordinate system. So don't try to think of them as totally equivalent if you see things like that. If you were going to try, maybe you're not that type of person. So again, Lagrangian, right? Lagrangian is I affix my view at every molecule at a time 0 I've defined. I solve the equations. It integrates forward. I see, and I look at the paths. Here, you take your body of fluid, you subdivide into every single, into every single point in space, and then you just look at those points in spaces and then see what happens. This ends up being a good way to describe the motion fully. Okay? So sort of, more I have this. Little sort of flow chart, right, of what you get if you were to do this stuff. I don't like walking. I might just grab my notes now, right? So then this idea of have Lagrangian viewpoint and the Eulerian viewpoint, okay? Both start off some region of fluid. Both cases we've done this. Again, keep an eye on this maybe notation you haven't seen before. The idea being I have a region and I just keep breaking it up. I just keep breaking up in little bits and bits and bits and bits. Okay? Okay, then you assign some P naught point at 0. Here, vector point time equals 0, and there's temperature. And then what do you do here? Really, you do the same thing, right? Still do this subdivision thing where you just now assign initial pressure, initial velocity. Those are assigning things we'll talk about later. And then maybe really the difference of sort of happening is they'll do the same thing, but the interpretation is sort of different. You put this into your equation of motion. Okay, and then what you end up getting out, right, is the idea, the solution for something like this is just a giant set of vector paths right, for the Lagrangian, and then Eulerian okay, this will give you this description. And then a temperature as well. So maybe a little stranger to interpret as, right? But the idea is like it started off the same. You broke up everything into little bits of volume and little bits of fluids. You then assigned initial conditions and boundary conditions. We haven't talked about that yet. And then you jam them into the equations. And then what you end up getting at the end is you have this idea of integral curves which come from the vector field, or the vector field coming from the integral curves, what they're commonly referred to as. Okay, two different things. They're equivalent, though, right? And maybe already it's interesting that just from the study of fluids, you have a better understanding of what this of terminology later is, right? Because it's something that's called a fiber bundle, even. You might see later, and this is vector fields are just common ideas. This idea that my vector's assigned at the points of my coordinates in time, or I just look at some initial condition and I can just draw out these curves, right? So this defines some field, and what this then defines is just a giant set of just curves existing in space. But they're equivalent and they're dual. But now let's move on to final. All right, and that kind of establishes a neat sort of natural choice we should make when we talk about motion. And let's see why that is, right? So now that we have these two viewpoints of how to describe our bodies and our coordinate systems moving in fluid, time I have, good. Now let's talk about motion. Okay. Just moving forward like that, right? Let's talk about motion, right? So motion is now sort of no math sort of terminology, or really it is, but we're talking about like physics now. This idea, right? Physics, right? This is sort of the language of change. Okay? Motion is fundamentally about something changing, right? Motion is about you were here at one point in space, and then some time later, you're now here at another point. So you will need some concept of change. You'll need to talk about derivatives. i.e. small changes. So we have, right, it's not quite the same thing as what you learned in calculus, or, right, of just single variable functions, or sort of even multiple variable functions. You maybe learned about these ideas, but, right, we need a better way to talk about this d change in time, right? Because motion is really about change in time, right? That's what right. That's all of the equations of motion we talk about. Is time is now, time is later. What's different from now and then? How do I predict the future? So that's how we have to talk about it, and that means we need to talk about this. Okay. So again. Do it here. I have any established coordinate system. So we have any established coordinate system. Okay, this is my body of fluid, right? And we had two different terminologies we could have. Some region. Right, what was this? That was my little tiny bit of fluid. Here's the big bit of fluid. This has some sort of boundary. If we talk about a box, you need to assign things at the boundary as well. Okay? And then, right, you have this idea from my coordinate system, I can talk about stuff. This is sort of R, or an X dot, or X bar dot. So this is how I talk about things. I draw a vector from some origin I've defined and explain things, and then you have some sort of path that will exist. Okay? So then, in terms of that path, you could have any property, right? So I'm going to talk about F really could be either a vector, it could be pressure, or it could be temperature. It's some property of the fluid that I'm tracking. Okay? So I'm tracking some property. I'm going to use a generic f variable to describe that. If I'm talking about the Lagrangian viewpoint, f of L, right, that would be some initial condition and then my function of time. Right? In this body, if I'm talking about the change of any property, what you're really describing is this whole path line as a function of you give me an initial condition, and as time ticks along, I will exist on some sort of path coordinate. Right? And then differently, if I just focus on my center of mass of my d theta, d or di, right? This is some property E. Okay? And I'll just say this is a function all around. An x, a y, and a z, and then the t. Okay? So we have two different ways to talk about change, because we had two different viewpoints of talking about the body. Okay, so then let's look at right? So you need to accept the idea that if I write derivatives, this linear change of et cetera, you learned about if it was multivariable, you could just add up the contributions of each component linearly. So that talked about partial derivatives. I'm assuming you had to take vector calc for this class, so I'm allowed to write this, and you're OK with it. Some of these things are not totally well defined, but they get the point across. Okay? For the Lagrangian point of view, right, what happens is, right, I have this change by chain rule. I'm adding up to certain things. And you could actually, some people even have this idea of some t naught, right? I think Pan did that too. But let's say it is like that, where there's some different time parameter like this. I think that gets confusing, but I'll put it up here just to make sense that really what you've done is you've just done this chain rule and added up the linear contributions. It's like the linear theorem of multivariable calculus. You can maybe just look it up in your calculus book you just used for PSU, right? Importantly, though, what happens is that since I said that in Lagrangian viewpoint, I affix my initial condition, and that's it. It's just some number I put out of x, y, z, right? It didn't change in time, right? So this goes away, and then you have this sort of, that the change is proportional to sort of this path change. And then you have this idea now of these tangent vectors along, and that would give you that change. Okay. This alpha being this change of my parameter and change of time. Okay, something else then we have. Let's look at the Eulerian viewpoint. Same idea. You just run the same process, but now since I have it being just an actual function of the x and the y and the z and the t, or the r and the rho and the theta, or the rho, the theta, the psi, et cetera, it doesn't matter, a function of each coordinate point, you'll now have this situation. Now is about the time when people start to use index notation because it takes less time to write it on the board. But to the best of my abilities, I consistently have to do it first each term. Okay. So now what changed is you didn't have this idea that the initial condition point was just some point in space. Now what changes is that these x's and y's and t's are changing as we move along, right? And I just took up the additional contribution of each, and I did chain rule to get here. Remember in the first lecture I said your tool bag should involve chain rule. It's because you do things like this a lot. Okay? So now this, and this, and this, right? Look at these terms, right? These are velocity values, right? A dx dt is a velocity from physics 1. A dy dt is a velocity from physics 1, right? So you go like, aha, those are velocities. So you get this other idea, well, that would be, right, some u, right, a y velocity, z velocity. And then you still have this sort of change as a function of time, right? So now this change as a function of time is I'm just looking at this point, and I'm just seeing how that change varies in time, right? So if this is a vector emanating out from here, you can just see graphically that as time moves along, this vector tail is affixed to here, but then at a different time it will look here. At a different time it could like move down to here, etc. Right? So this is some, I gotta draw that one better. But the idea is you take, right? In this change in time, right? If it's velocity, right, what does this term mean? This is how this actual point changes in time, right? So this is at 0. At some other time, what if it moves over to here? Right? How does it move over to there? That would be a different time right here. So see how this vector sort of switched all the way over there. And that's affixing it at that point. That's what that would be. All of these terms now are talking about everywhere else that's occurring, right? Right? This is the convective term. So this is when it moves along. So think of it as the change of the center of mass of it, and then the change as it moves along its path. So they are equivalent, right? This is still moving along the path. Right? It's just change, right? It's just difference of how it's changing. So then there's this u and this v and the w. Those are the velocities occurring right here. So that moves along this path. And then this talks about how those change along the path. Right? And that ends up being a better description because you can fully characterize any little point, and you can characterize your whole space of x, y, and z. So we use that thing so much that we give it this name, right? So this whole vector notation it looks like that. If you were to describe the exact same thing and just use your vector notation, you would describe it like this. And this is so common that we take it and we call it some differential operator, right? So this thing, we're going to say I now have capital D, and that we call substantial or immaterial derivative. Right? Where this is equal to this derivative operator this. This is the material derivative. This is the material derivative operator of right, operating on some f, and this is just the material derivative operator. Right? It's awaiting to eat something, either a scalar field or a vector field. But right, that derivative operator is how we're going to talk about motion. That's the operator we need to use. Now, this is what is amazing or has developed so much interest in this Navier Stokes equation. You see how our derivative operator is defined now in terms of a velocity field, the x, the y's, and the z's, that are only talking about the coordinate system, right? So first, let's say I have some scalar field. Okay, temperature is a scalar property. There's no direction associated to a temperature. I'm just 20 Celsius. I'm just a value. I just put it in my Arduino and I look at that voltage reading. No direction associated to it, right? So let's just okay. And I'm operating on some scalar field. Okay. This is now this idea of a function, right? So scalar as a function of x, y, z, and t. Okay. And then you just do this out. So here's the change in there. Okay. See how that worked? You just do it out. I guess I missed one more step. Really, see, you notice sort of expanding this out, really, because this is a vector of u, v, w, and this is a vector of derivative operators, so that's this. A dot product is a sum of terms. and you would operate then still on the xy, t, then you would get just that expression. Oh, all right, again, I'll just actually do it right here. Right, t goes in, t goes in, t goes in. Nothing wrong with it, right? The operator worked just fine because I just multiplied through. I just did multiplication of terms. Okay? Here's the interesting part now. Let's talk about operating on a vector field, right? So now, let's have the change of velocity. What does that look like? What is a change in velocity with respect to time, whether I measure it with substantial, material, or just my physics 1 derivative, right? Change of velocity as a function of time is acceleration. So that's Newton's law. That's next. So dv dt. What happened when I did that? Well, boom. That is nonlinearity is the thing. That is what's going to make things so difficult for us, is that I have now my derivative operator defined in something operating on what it's defined by. So there's now going to be square velocity terms in there, making the equations that are telling me how motion works totally nonlinear, right? But it happened right from there. It didn't really happen here, did it? No. Because now I'm just using my material derivative to talk now about temperature. I'm nonlinear about this, but when it comes to me trying to solve what acceleration is, oh no, right? And you have to kind of be tricky with this where this, right, because this we're going to say is some, right, what was it? It's a vector defined by the u, the v, and the w, right? So then operating, I now have a u, a v, and a w. Okay, and then I will also have this, a u. I'm going to do this, x, v. Just do it like that in case anyone's confused. Right? Again, if you just do out that dot product, right? A dot product spits out just the sum of these terms, but it wouldn't be well defined unless I operated now on this. Still here. Okay. Okay. So we have now this is just the change of the u, the v, and the w of the center of mass of my body point. And now you have this situation where you now multiply this by the vector. But you have to think of this now as just scalar multiplication, because you can take a vector and then multiply it and then look at twice that vector or 3 times that vector. So you take your velocity vector and you scale it up by this by itself essentially, and write derivative operations. So that's nonlinear, and that's where a lot of the issues come from, right? And this is scalar too because, right, we're saying that u, v, and w, right, those are scalar numbers, right? My vector is composed of the component of velocity in the x, the component of velocity in the y, and the component of velocity in the z. So those are scalar numbers. So you can, it reasons that you can say this as just a scalar multiplication. These get tricky, but it works for the interpretation. And it also works to highlight where the nonlinearity comes from, where the issues are arising. Okay? And it's right there. You can see it plain as day, the idea that my derivative operator that I have to talk about for my body of fluid is defined in terms of how it has to be moving in the first place. Right? So you'll have to have square terms. Right? There are terms that are going to pop up that look like this. Right? A u and then this. This multiplication is what defines a nonlinear ODE. Again, for that grab bag, it was helpful for you to understand how to classify a differential equation because of things like that. Right? If you do some larger derivation like this and you can come around of doing how something's defined within itself, you go, oh no, nonlinearity. You know where to move from here on out. You at least know that you have a hard problem. Okay? That's something that's helpful. And then this is also important, right? So really we're just on our way, right? What did we have, right? F. Right? That's how I'm going to talk about motion. Right? And this being the motion part, this vector acceleration, right? sometimes it's helpful to think about this as right? My acceleration, my motion, which is the acceleration vector, the change in velocity over time, which happens to be nonlinear. Oh no, doesn't matter. We're just moving along to see what equations arise out. Is prescribed by forces, normalized by a mass. Now this mass will cause error, right? Because, right, mass for a fluid, we have to talk about now density, right? What's density? Well, that's this idea of mass and then a volume. I'll use this term for volume maybe so it's don't confuse it with velocity. A lot of people will do that, right? So this has an issue now as well, where now what I've normalized by mass is going to change because any volume or arbitrary volume I could draw would change as well. And then the forces is also difficult. So this isn't too hard to think where I have now right, some density, which is a scalar number, of velocity will be my mass. So that's what I would have to normalize by. Okay? So hopefully now you understand that we've gotten naturally to the idea of where this substantial material derivative is going to come from. It came from me wanting to talk about motion or change, and it came from me wanting to study your coordinate system. It came from me as the idea of a body, so I've assigned points where they are. And that's how I got my A. Mass, we'll just assume that it's understand that you could just have a density and divide and multiply it by some volume or region. So, right, volume or region, a body, a little body, right? Think of it like this now. Remember all that subdividing I had? Well, same idea, right? Any little sub-body I draw in my total body of fluid, that's a volume. I'm defining some volume of parcel of fluid. That's my mass I would have to define by, right? And then you can also see, oh, this is strange now too. The acceleration I now have to define at every single point in my Euler vector field. So this equation is going to define every single point in space. You're defining a vector field. You give me an x, a y, a z, and a point in time. I will tell you the acceleration. But you need to give me a point and tell me a time. So these little points, these volumes also have to be true throughout the entire region as well, right? This little point I draw right, needs to be a function of x, y, and z, and of t. Sorry, t as well. OK, so all this to say, this is next. Forces, right? I want to talk about motion. So now I got to talk about forces because those are what are going to describe my motion. Okay, and here's really what kind of brings in this concept of a fluid, right? Because there's just, right, we have to now talk about types of forces that we're going to talk about. So now we're moving into a fluid. Give me a clear board. I really got to work on my erasing to be on better pace. So now we're on to a fluid, right? And this is now where we have to talk about shears and normal forces, etc. We don't really have to do it here. I kind of realized later it's like, it's kind of still true for any continuum mechanic force, but really the strain is really about a fluid, so maybe we just replace this with force, actually. So we have to now talk about force. Okay, forces. Right? So we moved along. We've subdivided our region, capital omega, into a bunch of little capital omegas, which are little parcels of fluid. Each of them has some center of mass I'm good on time. A center of mass that I can imagine. All right? And now we have to talk about, well, how would I describe forces on that situation? So 2D is a fairly okay and easy one to do, right? If I just have some 2D region, right, my coordinate system for this one, I'll say, is here. Okay, and this subdividing thing here is the region of fluid. Let's say here is my boundary, right? All the set of points that exist on this line, you have to assign as well for any sort of differential equation. So then subdividing is this process here, and it could be any way I just want you to kind of care about. I could partition this any way I choose. It might make my life a living hell, right? It could even look like something like this. Okay? So you just kind of, you've broken it up, and maybe you've done a poor job about it, but then you have this 1, 2, and there's all over. Like, let's say this is now my last one I've counted at the very corner. So let's say I count this way. You could understand you picked one. And this is really that notation I had before where, well, then that means that this is really this sum of all of these regions. That's what I was really mentioning, that idea of subdividing, okay? So process we're going to do is I want, this idea of this is true, then I can describe all the forces occurring on all of these. And then if I use that concept of Newton's third law, right, what was Newton's third law? It's conservation of momentum. This idea that all the inner forces will have to cancel out. So if I sum up all of these things, the inner forces cancel out because momentum's conserved, and I would get the total force, the net force. Right? So that's this idea of sum force. Right? Of all of these, surface forces, etc., will give me the total. And really, in the process in your head, what you do is you should be thinking of it this way. Right? You just kind of limit. Right? This was an n, and what you do is you keep subdividing such that if I do more and more and more of these things, it's just smaller and smaller and smaller, and then I can talk about integrals. So it's kind of a common, hand-wavy trick. You just take discrete sums, look at the math of that, and then make everything smaller and smaller and smaller region-wise, and then you talk about integral. But, this idea is if I have some force here, well, there was a normal, and then I have sort of forces here, right? But then in these surface or interaction terms right there, you then could tell yourself, well, I also have the third law that will talk about the motion of Newton, which is what? Equal and opposite reaction. So that means it would be a telescoping sum. Look that up, right? Whatever, just look it up. That you'd have now this one, and then maybe you had how this would move outward, but how these inner ones would cancel. But you do want to talk about the inner ones, so there's tricks about that. So that's just the 2D version. But I want to talk about how we do subdivide, because it shouldn't matter, right, for how we're going to talk about infinitesimal things. So usually, right, I've been drawing this the whole time, a little actual cube. Why did I draw this little cube, right? Where this is my region. Right? That's convenient, really. You could really break it up into some sort of really strange oblong bulb, right? Something like this. Okay. And that it should still be true whatever I write down on any of these. I could either draw these cubes or I could draw this, but as I go further and further down a length scale and make what I'm considering smaller and smaller and smaller, it shouldn't have mattered how I broke this up. Now, what's nice about a cube? Well, a cube, as a surface, right, it has a normal vector here, here, right? You can define the surface, and remember that center of mass point, let's say, for here. So here's like 1, 2. This only has 6. It only has 6 normal vectors. Right? A cube can be defined by its sides, right? A side can be defined by a normal vector. And then it's a normal vector, and then an area. Okay? Normal vector and an area. Normal vector and an area. So you could actually say this thing is defined by 6 vectors. Okay? 1, 2, 3, 4, or 8. 8. I think it's 8. What have I done? Oh my god. No, it's 6. Oh my god, I'm so sorry. Right, so this also can be defined if I have those vectors and scale each of these vectors up by the area of the cube. It would actually be the same, but that's this idea of oriented area. Right? If it's really small, this is a small, tiny cube, so this would be like 3 nanometers squared, let's say, physically. Right? It's small, so now I take my point, and I would move 1.5 nanometers away from my center of mass, and then from there I have some small area. That gives me directed area, oriented area vector. And all it is my normal vector defined there. Then I have a dA, which is a scalar value. Scalar. That is really this idea of oriented area. So that helps. But for this one, too, the same thing could be done. I could have some center of mass here. And instead of just actually 6, I could go anywhere. Right? I could go for my center of mass and look at the surface of this thing. Right? And I can draw a tangent plane called a TP. And this tangent plane, right, it's a plane because it has some normal vector defined for it there. Same idea. The only problem with this is since it's a nice smooth surface, right, we have an infinite number of normal vectors because every point there's going to be a normal vector there. So it's just hard to describe what's going on. But regardless of if it was 6 or it's an infinite of how I've limiting these things down and more and more and more, because what you do is you take this volume and you shrink it. It shouldn't matter. So that process of this one could be all the way an infinite number of normal vectors. So it's a little more difficult to describe what's happening on every face. Okay? And that brings, however I decide to define forces, there's 2 types of them. Right? Right? There's a volume force, or a body force, what we say, and that force is dependent or scales on volume. Okay? Surface force should be, right, is going to scale by surface area. Right? That's this idea of shear or of pressure. Okay? The more volume you have or the less volume, it's dependent on the force. Right? So for a volume force, gravity, right, any sort of other field, right, gravity right, gravity and electromagnetic fields are classic examples in fluids because a magnetic field can prescribe a force on the actual body of fluid. Right? Gravity you can understand too because the more you weigh, the more you weigh or the more you weigh, the bigger the force, right? And that really is a statement on density. But it doesn't matter what, right? It doesn't matter the surface area of you particularly how much you weigh and the force it is. It only depends on the actual volume or mass that you are. So volume forces, right, are dependent not on anything about surface. They just depend on the actual mass or volume that you draw. Surface area depends on the surface area itself. So that depends then on these dAs and in D1, dA1, dA2, dA3. The more surface area, so these are, right, a pressure or a shear, right, are surface areas. Okay, one other sort of thing I talk about, or I think of myself, where I think is that the volume is some function, right, of the whole region itself, right? If you forget, don't like the omega, right? Think of it this way. That, right, a volume force is a function of the little bit of volume, right? Whereas a surface force needs to be a function of the little bit of surface area. So then it's sort of categorizing how do I characterize that surface area force. I want to know what that function is. So you can dig deeper. You can peruse and look more then about what the surface forces are. I'm going to leave this sort of just alone because it just depended on the volume itself. But I'm looking at surface forces. That's what I care about. Okay, so whether it be a tangent plane, whether it's one of the 6 tangent planes or the infinite number of tangent planes I have, right? The tangent plane. Right? And then I have my normal vector, and this is some strange body of fluid. Okay. And then, right, if there is a force happening on here, I really would like another color. That would be good. Force is a vector. It has to have direction, right? This is the idea that I can break that force up, I can decompose it, right, into what? These two tangent vectors define the plane or the face of the cube, right? And then the normal vector defines the other coordinate, or the vector that is perpendicular to both of these. So then this will be able to decompose into that regardless of what coordinates or what, right, or how either it's a cube or something like that. It's just a tangent plane. So any force, which is a function I want to say of a little bit of area, must be decomposed, right? So right, normal forces, or ones that are right in line with my vector n, would be right the force dotted with that n vector. Okay, and again, the thing is, this normal vector is a function of some point in space. Right? This is going to be my p naught, right? Right? That's my p naught. It's a function x, y, right? It's a little point in space, a little x, a little y, and a little z tag. So forces are normal would be this situation where I dot my force vector, whatever it is, in terms of n. Okay, and then you have forces that are tangential, forces that exist on the tangent plane. Right, where this is just an orthogonal relationship. The idea of this plane, I can define R2 in terms of 2 perpendicular vectors. That would be my T1, T2. These, again, are defined in terms of this point. These 2 tangent vectors are a function of whatever point I've been given. So that these forces would be, again, my arbitrary force that's going to happen on the surface, right? And then I would dot it then with either one of them. And I could get then these surface forces occurring. Right? So what does that mean? Right? At least we can have a, right, we could at least count, right, some things now. Right? Because, right, for normal vectors, right, this is just a normal vector, but I know it would be true for any sort of, right, vector I have now. You could use, right, you could use the unit vectors in the x, the y, and the z, or a unit vector for rho of theta, et cetera. But you could dot the same force with these, and then you would get exactly what that is. Same thing with here. There are 3 perpendicular ones in the x, y, z, 3 perpendicular ones in the x, y, z. All this to say that in order to do what I'm trying to get at, I need some way to describe I need some way to describe 9 forces occurring in my vector field. I need the ones to describe that they're normal. I need to also describe these 2 tangent planes. And as I limit it down and down and down, it still needs to be true wherever I am. Even if this gets arbitrarily small, I still want to retain shearing forces on all of my faces, right? So that's tricky. All right, I'm doing on time right now. Okay, I might move a little bit forward. I have a look at the notes. There's kind of a better graph I maybe sort of try to draw on this concept of I have a big body of fluid and I draw some region, and I could just sort of look at any of these tangent planes, but I want to be able to describe them, right, for anything. But that's really what's going to get us now to a big concept of all continuum mechanics, actually. Really heavily relies on this object, right? And it comes from, darn, I have to describe 9 forces anywhere. It sounds just... And I call it this, capital sigma. Okay, that is what this stress tensor is that you maybe have heard about before. It's the object that lets me define the 9 forces occurring, right? All the surface forces and all the body forces at any point within omega, a body of fluid, right? So that's just conceptually what it is right there. And I haven't even given maybe this linearity or things like that. I kind of like this idea that we're just sort of searching now for some object, right? All I said before was the thing I really want is, right, my function, some function of little bits of area. Oriented area, too, is what's important, right? And that's sort of this idea right here. Even though this is a really, sort of oblong body, right? Right? If it's smooth enough, if I zoom in further and further and further close to there, it will eventually look like the Euclidean 2D plane. It will just look like a 2D plane. So what that means is if you were to zoom in further and further, you would get to the square case. Okay. So see if I were to zoom in, right, real close up to the surface point right there, that eventually I would get to a very tiny bit of area, right? But I would still be normal to it, right? This plane still has this normal vector regardless of the size I draw it, because a plane is just defined. And it still would have these 2 tangent vectors. Okay? The idea being I zoomed so close up that I did get to the cube case, that I did get to that flat face situation that you normally see. And that's this, right? So this is dA. This is a scalar value of just dx times dy. It's on the surface. It's still defined by here. So any surface force occurring at this really little tiny bit of area element, I want to know something about that function, right? Again, remember now, I'm going to talk about oriented area, where the oriented area is really talking about this dn scaled by the dA, right? So dn is equal to the normal vector times dA. So, right, if the normal vector looks like this, if this is, right, again, normal vectors are unit 1, right, so that's 1. I've zoomed in extremely close, so you can kind of actually imagining this dn being just like right here, right? It's super small because dA, right, this number right here is small. I had to zoom in super duper close on my oblong body. So that would mean that this thing is shrinking really close. So dA is a small, very small, tiny vector because you're talking about little bits of area. So that's your goal, right? Stress tensor comes about because you want to say, right, that the force vector, the arbitrary force vector occurring at any point, x, y, z, function dA, and what that means is some function. Okay, that's what you're claiming. And it makes sense, too, because the function, right, a surface force is clearly some function of surface area. You've just stated it like this. And you've also stated there's got to be 9 things, et cetera. You have enough pictures to kind of maybe move forward on how you would do something like this. But now you're at an impasse, right? I think so. Right? Because now you're not stuck, but you're going like, oh, right, OK, now I have enough terminology. And I've said that I'm really looking for surface forces. I'm really looking for any forces, actually. It's so general, it looks that well, that you're sort of there. So how do I say something about what does this look like? Okay. You know how you're going to prescribe motion. You know how motion, right? You know how the motion's really occurring. But you're now at this part where you go like, I now need to see what does F look like. And that is sort of my argument when I think that like, right, you have to use some amount of math to show something because you wouldn't really know. And all of this is really going to come about from this limiting process of scaling things down more and more and more, and the fact that physically we accept them to be true. That's not true at all, right? We know that if we scale things more and more and more and more, down and down and down, it's not true. We won't have classical mechanics laws anymore. We'll have to get into quantum stuff, et cetera. But in terms of this modeling situation, you are saying that whether it be big or whether it be small, I want to have the relationship scale the exact same way. So all this proof that I'll do that maybe will just be a disaster will maybe just be generated like this. So, right, one great way, one nice thing is just if this function is a linear function, okay, linear in its arguments. And that's nice. That's one of the nicest properties of a function that we have in math, right? So here's the property of linearity, right? This is what linear means. So you're right. If rhymes right, I want to suppose, I want to hope that something is linear, because then I have better ways of describing it. Okay. And this is really with the index notation and like all the Panton, or maybe if you read in the book, he goes a lot over like not this, but he really goes over like it's a 4 index tensor, it's a 2 tensor. It's this idea of breaking down being able to describe a function in terms of basis vectors is where the index stuff is coming from. But I don't, I sort of see it as you only trying to characterize what this function is. And I think the easiest characterization of any function is it being linear. So let's try to prove that this function, which I know is a function of the areas, is a linear function. Let's try it, right? Now, a couple physical arguments will come into here because I'd be stuck at a couple points. One of them being that I'm looking at really small bits of area, and one of them being that if I limit things slope more and more and more down, it's still going to be true. Okay, and there's even more assumptions that we'll show in. But the biggest one is I'm looking at a function. I'm looking at this function as this limits down to 0. So I'm looking at the function around when this argument is really small. So that gets you to this Taylor expansion. Okay, I'll assume then that my function, I'm looking at a function, the scale. I'm going to keep this random parameter here, which is really some sort of scale, right? And around this dA. Now this will be a little bit weird. So let's just say A as a vector. because I haven't gone to dA yet. What did I have here? OK, so I'm going to say this looks like, this is just the Taylor expansion, by the way. So if this is going down, what does it look like around the area being 0? So that would be A, that's A var being the 0 vector. So that's f of z, and then I have this by a chain rule. Right, A. Maclaurin series, et cetera. But you have just Taylor expanded, and I'm saying, what does it look like right around 0 area? Right around when this thing, right when this vector shrinks down all the way to the 0 vector, what does this function look like? Because that's what I want to do. I want to break my volume up into little tiny, tiny, tiny infinitesimal bits of surface area, and then I want to integrate over them, and then I have the sum of the total forces, which is this, right? And I know that the, right, et cetera, right? But you're getting at this point. So 0, OK? This, right? Oh, this came from chain rule, too. Remember, I told you you want that chain rule deep in your math tool belt so you can pop it out any time. DFDA, right? This is always nice. Just like look at the definitions, right, if you're stuck. So here's the f of the A. OK, it's a little bit tricky. Let's just say, for sake, this thing cancels out. I have some scale right here, and then I get this. OK. That's what my function is going to look like around 0. I've made an assumption here. So my assumption I made for this little proof, and it really gets down to like all of these assumptions of the tensors, et cetera, is this idea that this function of how I'm assigning forces is a pretty smooth function. You can't do this, right? Not all functions are Taylor expandable, right? It's actually a pretty small, limited set of them. But we've done that here. So, right, and it's kind of strange, I think. I mean, certainly turbulence doesn't look that, right, at least that we know. It doesn't look like, it looks like a pretty discontinuous sort of process, right? It looks almost quantum if you look at the graph of voltage measurements. It's just all over the place, right? So maybe that broke down here. We don't really know. Certainly if you zoom in for and more and more. I mean, it's even worse, the fact that like I did zoom in to 0, so this would still be true regardless of that. The only problem is the function is the assumption, right? It could be a nonlinear mapping of surface forces. The proof relies on how smooth you assume things are. And then we're not done. The idea here also is what? Saying, what's the surface force at no area? So what's the surface force at no surface? I say is 0. Okay. Again, right? There's no surface, right? If I'm looking at some surface force of dA, what's that function look like? This ends up being 0, so no more surface force. So you make that 0, and that kind of did one part of it. Right? So neat little thing, right? We looked at a function close to 0 area, and we showed at least this part of it. Okay, not done though. This doesn't prove linearity. You have to talk about now sums of things. You have to show me that the function, you can either scale up every surface area force and then get it, or you could look at the scale of all surface area forces, apply the function, and get the same exact thing. You already kind of see how with calculus these things would maybe be true regardless. OK, so then next I have to show this idea of the summing. So remember, we have shown this. For any argument, I can scale it that way. But I need to show now that this sum works out. OK? And I have this little thing here. Look at this now. Again, maybe I've done this zooming maybe too close. If I have some arbitrary body, right, like this, right? This is a little bit of area, this is a little bit of area, right? And just think about like length scales. Here's some, let's say, if I have some little region of fluid I've drawn, and I mean that this is the surface area that I'm kind of filling in, right? This fact that the mass of it, right, is equal to rho v. And I'll say that really scales, like let's say even if it was compressible, right, where the density could change, it would scale by some characteristic density and then L1 cubed, right? Even if this doesn't really look like a sphere, you may, right, even if it doesn't really look like a sphere, in terms of like on an order of magnitude scale, you're saying, it doesn't look like a sphere, I could maybe draw a sphere close to it, right? And then I could, right, the scale would still be a third power, right? Just look at the, right, the volume of a sphere is, right, it's, right, 4 pi r cubed over 3, right? But those are just numbers in front. The idea is that there was the cube relation in terms of your length scale. Okay? And then area, surface area, sort of also the same thing, of the entire thing would scale by the square of this L1, right? Just, right, 4 pi r squared. So same thing on the scale of this big case right here. But then also keep in mind that I'm saying that this is equal to the sum of all these little areas. The whole surface area is going to be composed of a bunch of little squares I build up from smaller and smaller things. If it's a cube, it's a pretty easy sum. It's just 6 sides, and that's your surface area. Okay? But then on the limiting case, this is what I talk about with like this getting smaller and smaller, right? It's sort of your largest dimension is getting smaller and smaller and smaller. Okay? So this is L1, my biggest one, and I look at it closer and zooming it further down and down and down. So now this mass is scaling now as rho naught. Okay, and then this mass surface area. Okay, and then you get to here, right, where really you're saying this is now going to 0. I have no more surface area, right? And then the mass is getting no more surface area. You're zooming closer and closer to a point, and this is the process that's happening, right? Regardless of how I drew it, you kind of bound above. Let's say if it was really wiggly, I could sort of like draw a largest sphere and a smallest sphere that this could exist in. So then that would be the mass being of, right, of L1 cubed, the area being of that same dimension. It's got to be around there. It's got to be around there. And this process of going further and further down to 0 is where some of it is where this next part, I think, is heavily reliant on. And there's another thing that this will be reliant on, and that is the sum of all we also rely on the fact that for any closed surface, this, right, and I say the little d, right, I say this d, right, dA, because this could also be true for a very, very polygonish type of surface. But we say that the sum of all the surface areas of oriented surface areas has to be 0. Okay. Now that comes from really, right? Really, it's Stokes' law, where that's going to come from with a constant vector field. So I can remind myself of this if I look at, right, the divergence theorem even, right? An integral of any vector field dv there's an n there. I even do that too, right? Because I know a dot product between two vectors is a scalar, and then this is a dot product, which is a scalar, and then volume's a scalar, so I go equal, equal. And then the idea, if it's a closed surface, say our cube, let's say, okay? If this is a closed surface, so all the surfaces sum up and there's no open bits of area, there's no undefined outgrowing region, right? Then if you looked at all the normal vectors and scaled them by the area, it would be 0, right? And one way to show that is if you had any of these, right, well, this vector field is a constant vector field, right? sort of you looked at it for every sort of, right, if you looked at this case for every normal vector, right, really what you're doing is you have like this, right? It's sort of at any one of these you want to define, it's going to end up looking like that. That means each component's 0. This is going to be, this is right. And then you make integrals into discrete sums, and you can show it that way. Maybe just to convince yourself. Now, I would say, just from, you know it's going to be true, so then I'm going to give this extra credit. Do the explicit calculation for a cube, right, where you have a cube sitting with a corner at 0, 0, 0 point. And make it any length you want, actually, and show that this would be true. And since it's a closed surface, and I sum up all the oriented areas, that it's equal to 0. I remember it's through Stokes' theorem, and I proved it's a more math thing to really prove if you want to do that. It doesn't really matter since we're a fluids engineer world. I think just sort of hand-wavy stuff is OK for this, because we're just trying to get a sense of what we're trying to model. What's important, though, was what I was trying to describe what that function has to look like and behave. I got half of linearity down, so let's move. So we have to get further than that. So, right, I use that oriented surface law. Right, this equal to 0. One other way of saying this. You just move 1 over to the right-hand side, right? I just took an equality equals 0, and I just moved 1 over. And I could have picked any one, right? You could have just had a j here. You just need to make the sum correct. OK. So, right, that's geometric. That has nothing to do with physics at all. Here's where the idea is you still then say, let's look at forces. Let's look at it that way, right? I know that the sum of the forces, I have one volume force defined, right? And you could be a sum there too, right? I have volume forces and surface forces. So maybe like, let's say sum all of them, that's going to be equal to this MA, okay? And here's where the scale thing will come up. But again, think about that. We're trying to prove something where we've drawn in this law from Newton. It has nothing to do with math now, right? This is an assumption based on physics, not of math. Try to separate that anywhere when you do something in a fluids classes. Where was the assumption based on a physical law, and where was it just in a mathematical operation? I will tell you that that material derivative was not physical. That's just a property of having to describe the domain. And there's a subtle concept there, I think, that people don't think about enough. Either way, moving along. We've got the sums. Now let's do it this way. This is going to be right? I know that this sum is saying this, okay? And move this over to the left-hand side, okay? A little bit of volume, a little bit of surface area, okay? And now, when we go to that scale picture in our head, that's where we use this idea, right? This has to be true regardless of the scales. Now it's an F, and I have an L squared surface area, scales. Any scale I want to put, this has to scale like the L on there. Right? And this is a component by component summation, right? Now, component by component, I already showed the last step that I can pull this out. So now I get the L squared, right? Because this was a component by component sum. So that's where the L squared can be pulled out one by one. This being constant is just the basis on that. I've scaled it by the largest dimension in every case, right? I'm just saying one number to scale my whole region so I can pull it out in that argument. You can't do it if it's different for every single A. But if you make one scale, the largest scale, let's say, the maximum scale that your region has to have, allows you to define it as one number and pull it out in front. Okay? And then on this side, we had this mass argument, rho naught dv. Then you had some a vector as well. Doesn't matter. And then there's volume right here. Same thing. Clearly, right, the same idea. You would make the same Taylor, right? You could make the same exact Taylor expansion idea on this thing to show this one case here. Now, linking up these is key, though. Right? Okay? Because this L was the largest one I had, and this was the square. So I have surfaces, and then I have volumes. This is the key, though, right? Because the surface side only has a power of 2, this one's of 3, so you could cross this one out, right? And what do you have, right? Now I can make the statement saying, I want to have L go to 0. Right? As L goes to 0, as my largest scale of my little volume of fluid, maybe look back at that picture of this thing getting smaller and smaller and smaller. What you get now is that this was 0, so this whole gosh darn thing is now 0, right, in the limiting sense, and I have that, right? Because there was an L left over based on body forces and mass. The functions that were dependent on the size of the object I drew had an L cubed in them. The surfaces had an L squared in them. I had one left over on the right-hand side. I said L went to 0. I get this 0 now. And this is a term-by-term sum. Okay. Same trick now here. Use that. Right? Using that, you do the same process where you say, if I had n of them, okay? You just moved one over, right? Now, this is just the same constant I had lambda. It was a parameter in that Taylor argument. Lambda didn't have to be small, right? It was a that was going to 0. A was just some, right, lambda was just some sort of scalar thing I had there, which was the magnification parameter I had, let's say. Right? So that can be 1. So this is a specific case, right, when lambda was equal to 1. But I already showed in the component-wise, right, that in this sense, when this number is dropping to 0, I can have that be 1, and I can put that in here. Okay? And then you go here, and then you have it. Right? You showed that last. This part coming from the closed surface theorem we had before. This part coming from the idea that in my limiting process for small continuous bodies that I can have one L left over from. And then this, right? And then this lambda scale, right, of one constant value being able to be pulled out. That came from, again, right, that came from, again, this Taylor expansion process we had done. But the big old blammo result is that you showed right, that you showed, I'm getting tired, you're getting tired too, I bet. Right, the fact that you showed that F is linear given the assumptions of smooth, fluidy cases I gave. Am I doing on time? I am going on time. Right? So that's awesome. And I think a nice sort of, right, however I want to describe this process doesn't matter. What does matter is I at least know that this function that assigns me surface area forces, right, that assigns me forces at a given point is going to be linear in this continuous smooth case, right? So then sort of one other way that maybe is more higher is this idea now, well, that means that I can take any oriented surface, right, arbitrary, had no idea what was going on, prove something that it was linear. That means that I can represent it as a matrix. It's 3 dimensions and of 9 components. The idea that it's a linear functional of these area elements, that means that it's going to be represented by some matrix. Because forces had vectors, so this stress tensor talks about forces, which are vectors. So it means that I have to have any sort of thing like that. And these are 9 elements. Now, this is the stress tensor. Okay, that is the stress tensor that you maybe have heard about before. If not, then you certainly just see why it exists and where it is now, right? Stress tensor that you will hear about, and it's important for all continuum mechanics. It's the object that I know to exist because I showed that f was linear, right? And it has components. So there's usually say sigma 1, 1, sigma 2, 2, 3, 3, and then you have these taus. Okay, 9 components now, right? This means it takes some vector, right, a dA anywhere, right? It's just that it doesn't matter what the thing was. In terms of forces, it could have been a little vector of area. You can't have a vector of volume, but you could have that just the function itself is linear. So then this will take a dA or a normal vector or any sort of vector it eats, doesn't matter, and spit out something. So now comes you can kind of interpret things with like example calculations. It happens all the time. Okay, if I then take this stress tensor, multiply it by the unit vector in the x direction. There's a picture for this. My hand's getting tired of drawing pictures on the whiteboard. I do it on paper. Look at the paper maybe as reference. Right here, what are you going to get there? If you do matrix multiplication, this says okay. So a little tricky, right? This is the I've dotted now my stress tensor with the x direction, okay? And then you got these 3 components. This one being the force in the x direction. This one being the y component. This one being the z component, okay? And that really shows you these parallel concepts right here. If I do have some body right here, okay, boom, here's some tangent plane, tensors, etc., normal vectors. Okay. And I have some now coordinate system. It just exists out here. Here's the body. Right? This stress tensor object, what it let me do is, okay, here's my force happening on the point I'm looking at. Here, this now tells me, right, here's the sigma 1, 1. Okay, maybe I can't, I need to draw bigger things, I think. So if I want, right, it's the decomposition, right? If I translate my coordinate system up to here, translate it up to here, so it's the same O. I've just like moved it, let's say, up there. So I've shifted my origin now to be at the point where this normal vector is defined. OK. Now I have this one. If here's a force here, right, what does the stress tensor do? The stress tensor tells me the x direction at that point. It tells me also then the forces that decompose onto the tangential plane. So I have a stress, and then I have 1, 3. And that's on a plane. Right? So any point. That's this idea. You draw that classical cube picture that you see a lot of what the stress tensor does. It's describing all of those components that exist on a cube. And those are the 9 arrows, right? And those 9 arrows are, right, those 9 arrows are defined by these unit vectors, and the scale of those vector arrows are given by the stress tensor itself. Okay? And you call this a stress tensor and not a stress matrix. You certainly could call it a stress matrix. But the idea is why it's a tensor is that this matrix, right, these 9 components are functions of points. Right? So this matrix will exist in every point of my domain that I'm trying to define where forces are happening. So it's not good enough to say it's just a matrix. It's not some constant right, object of matrix existing everywhere. It's a little bit worse where you actually have, right, it has to be different for each individual point within, right, within the omega. Right, x squared z point. And even if time, the stress could change. So even worse. Off diagonals are then things as well. Okay. So that's going to be the stress tensor, actually. Maybe it's not clear enough, the idea that it just was something, it's the function that tells me force is happening. Now, next lecture, we'll have to talk about the strain tensor, which tells, or strain rate tensor. And we have to talk about strain rate tensors because of that concept that a fluid can't support a shearing stress. There's no equilibrium at all if shear exists. So you have to tell me rate. If you tell me displacement per unit time, I can tell you the stress that assigns that. If it's a solid, you can just tell me a displacement, and I can give you the stress that gives me that. But with a fluid, it has to be a rate, right? How much extension per unit time? That will be the strain tensor. But I think similarly with maybe these arguments, and you can go over the notes because I think I write things with hand better than I say them. You can prove is symmetric. Right? You can understand even more about this f. Right? I showed that it was linear too, and that gave me the idea that, well, if I have any vector of x, y, and z, I can describe it through some matrix multiplication, right? Some linear transformation, et cetera. But you also can put more restrictions on this matrix. Right now, I just have 9 components. But this proof that the f also has to be symmetric, right, is now this idea where I showed that it was linear, and now you take the fact that it's a matrix and show that it's also symmetric. What that means is that the off diagonals are equal. Okay? So that means that there's not 9 components, that there's actually 6. So I've lowered the freedom I have of how to describe that matrix. Now this proof, actually, I would like you to, right, there's also extra credit, and I give extra credit. I give a lot of extra credits. Right? That proof relies on the same idea of sort of the techniques we did last time, where you limit scales down smaller and smaller and smaller and smaller. But with this proof you'll have to use is that's, right, angular momentum. Right? You have to conserve angular momentum. Right? Or just, not, right? You have to use, right, what is the F equals ma, but right, the F equals ma, but in terms of angular momentum is the sum, right, what is it, the sum of the sum of the torques is equal to time rate change of angular momentum. So that will involve a cross product, etc. I'm running low on Linearity, but I'm done. But you can do it. Okay? So I am running low on battery. I got to stop now. But we did get to 2 hours. I also have pressure has no whatever. Thanks. Next lecture we talk about the strain, etc. And we'll get even deeper. Okay? And then we'll have Newton's laws, and then we can move on with the class. I'll plug my laptop in next time.